Hello students, in the last lecture we complete operation on sets, operation on sets and most important De Morgan's law and number of elements in A union B and some questions on Venn diagram. So we start this lecture. In this lecture we learn about Cartesian product of two sets. Next thing is relation and types of relations. And periodic function. And some questions on periodic functions also in relation. Some questions. So let's start our lecture. Cartesian product on two sets. Let A, B are two sets. A, B are two non-empty subsets. Non-empty. Then Cartesian product is denoted by A cross B, and defined as A cross B is defined as AB such that A belongs to A and B belongs to B. So let's take example. Let A is a set. For example, let A is 1, 2, 3 and our B set is AB. Both are non-empty. Then we define A cross B Cartesian product. What is this? Collection of all AB such that A belongs to A and B belongs to B. Then 1A one B, 2A, 2B, and similarly 3A, 3B. So this is our A cross B sets Cartesian product. Now we discuss about number of elements in A cross B. Let number of elements in A is P and number of elements in B are Q. Then number of elements in A cross B Cartesian product of A cross B is 2A. This is only P into Q. In previous slide we can see here number of elements in A is 3 and number of elements in B is 2. So number of elements in Cartesian product A cross B are 6. 3 into 2. 1, 2, 3, 4, 5 and 6. Result verified. Okay. Now I want to one more question. Okay. Let A is 1 2 and B is AB. Okay. Then how many possible subsets of A cross B? Okay. How we solve this? We know number of elements in A cross B are 2 into 2, that is 4. Okay. And we know that our set is A cross B. Okay. We know that possible subset of A cross B are 2a to power number of elements in that set A cross B. So here is 4, then 2a to power 4 is equal to 16. 16 is what? Possible subset of A cross B. Okay. Yeah. Now we define one more example on this. What is that? Question. Our A set is 1 3 and B set is, what is B? 5 6 9. Okay. Then number of subsets of A cross B. How many? Number of subsets? Here 2 elements, 3 elements. Okay, so number of elements in A cross B are 6. Number of elements in A cross B are 6. And we know total number of subsets in A cross B is 2a to power number of elements in A cross B. That is 2a to power 6 is equal to 64. Okay. Yeah. Now I define now I define relation. Relation. Okay. What is relation? Definition. Definition. R is a set called be a relation from A to B if R is subset of A cross B. Okay. If R is subset of A cross B, then we say R is a relation from A to B. Example, let our A is 1 2 and B is AB. Okay. Then what is A cross B? 1A, 1B, 2A, 2B. Okay. Then R1, 1A, R2, 1A, 1B. These all are subsets of A cross B. It implies R1 and R2 are relations from A to B. Okay. A to B. Yeah. Okay. And it is 1 minute. Let me do a question. Find the, in this question, find the possible number of relations. Find the possible number of possible relations. Okay. Then what is this? We know relation is a subset of A cross B. subset of A cross B. Means we have to find number of possible subsets of A cross B, that is 2A to power number of elements in A cross B. Here 2 here, 2 here, it implies number of elements in A cross B are 2 into 2, that is 4. So here 16. Okay, there are 16 possible relations from A to B. Okay, yeah. Now I define description of relations. Description of relations. Okay, let A is a one set 1, 2, 3 and B is 1, 3, 5, 7. Then what are the possible ways to show a relation? First is elements direct written in roster form. Okay, this is our one way to show a relation. Second one is or. This is set builder form that followed a rule xy such that y is equal to 2x minus 1, where xy belongs to x belongs to A and y belongs to B. Okay, or third one is what? X relate to y if and only if y is equal to 2x minus y 1, where x belongs to A and y belongs to B. Okay, these are three types to show a relation. Okay, to draw a relation. No, whichever next to me, some note. What is your first note? If xy belongs to R, means xy is an element of R, then we call x as the image of x as the pre-image of y, and y as the image of x. Okay, image of x. This is your first note. Second is relation from A to A is also called or generally called relation on A. Okay, relation on A. Yeah, this is our now we define domain and codomain of a domain and range of a relation. Range of a relation. Okay, so domain of R is a set X such that xy belongs to R. Okay, this X goes to domain of R. Okay, and image of R is set Y such that xy belongs to R. Okay, let we define by an example. What is our example? Let A is a set 1, -1, 2, 3, 4. Okay, our relation is, we define a relation R from A to A such that X relate to Y if and only if X plus 1 is equal to Y. Okay, then this let our domain set, this is our codomain set, this also is, this also is. Here 1, -1, 2, 3, 4. Here also 1, -1, 2, 3, 4. Okay, then 1 is goes to here, x is equal to 1, then y is equal to 2, 1 is goes to 2. Okay, then -1 is -1 plus 1 0, here no 0. Okay, though there is no image of -1. Okay, when we take 2, x is equal to 2, then we get y equal to 3, then 2 back to 3. Okay, and 3 goes to 4. Okay, when we take x is equal to 4, then y get 5. There is no 5 element in codomain or in set A. Okay, so there are only 3 elements which maps in A. Then what is our R? R is 1, 2, 2, 3 and 3, 4. Okay, then 1, this 2 and this 3. R goes to in domain set. Okay, RD, that is 1, 2, 3. Okay, and what is our image set? 2, 3, 4. Okay, yeah. Okay, now we minute. Yeah, now I describe types of relation. Types of relation. Types of relation. And what is our important thing is there? On A. These relation are A to A. Okay, A to A. Only these type of relations we discussed here. Okay. Then first relation is empty relation. Empty relation. Second is universal relation. Universal relation. Okay, universal relation. Then third one is, 1 minute here, so learning types of relation. What is our third one? Third one is identity relation. Identity relation. Fourth one is reflexive relation. Fifth is symmetric relation. Sixth one is transitive relation. And seventh is asymmetric relation. Okay, asymmetric relation. Okay, these are the types of relation we describe one by one. Okay, then we start our first is what? Empty relation. A relation on a set A, this is our set. Okay, is said to be empty. Is said to be it's said to be empty if there is no element in R. there is no element in R. Okay, let's take example. Example is, let A set is 2, 5, 7, and if I define a relation X related to Y R, if and only if X divides Y. Okay, X divides Y. So here no element, 1 minute, X divides Y and X is equal to Y plus 1. Okay, means X not equal to Y. Then this is our phi set. Okay, because X not equal to Y, simply this thing. Okay, then 2 not divide 5, 5 not divide 7, 2 not divide 7, any of 2 not divide each other. Okay, what we get, R is 5. Then this is empty set, empty relation. Okay, then next one, second type. What is second type? Universal relation. Universal relation. Okay, universal relation. A relation R on set A is said to be universal if R is equal to Cartesian product of A cross A. Okay, this is our universal relation. Let's define A is 1, 2. Then what is A cross A? 1, 1, 2, 2, 1, 2, and 2, 1. This is our A cross A. And if this is equal to R, then our R is a universal relation. Universal relation. Okay? Yeah. Now describe third type of relation. What is it? Identity relation. Identity relation. A relation I on set A is said to be identity if every element is mapped, every element of A is mapped or relate with itself only. Here one keyword is only. One is itself and one is only. Okay, let I define one more, then I give a difference between identity and reflexive. Okay, so let I define first reflexive relation, then I give example of both relations, identity and reflexive. Okay, what is reflexive? A relation R on set A is called or said to be reflexive if every element of A is related to itself. Okay, here no word only, not here. Okay, only here, only. Okay, yeah. Then I give an example. A minute. Yeah. What is example? Let A is a set 1, 2, 3. Okay. Let I define R1. What is this? 1, 1, 2, 2. Okay. This is our R1. What is R2? 1 1 2 2 and 3 3, and this is 1 2. Okay. And what is R3? R3 is 1 1 2 2 and 3 3. Okay. Then we have to tell what is, which of the relation is reflexive, which of identity, and which of both. Okay. So this is set over. Okay. This relation is not reflexive, not identity, not identity. Okay. Why? Because 3 3 is not there. Okay. This relation is only reflexive, not identity. Why not identity? Because 1 2 comes here. Okay. 1 2 comes here, so not identity. Identity not. Okay. And this relation is both reflexive and identity. Identity relation. Okay. Yeah. In this relation, 1 2 not goes to identity, because in identity map only element is mapped or related with itself only. This 1 is related to 2, so this is not go to in identity map. Okay. Yeah. So what is our fifth type? Fifth is symmetric. Okay. Symmetric relation. What is symmetric? Let A be a non-empty set. A be a non-empty set. A relation R is said to be symmetric. Said to be symmetric if for all AB belongs to R, there exists BA in R. Okay. Or we simply say, if X relate to Y, then Y relate to X. Okay. Then R is symmetric. Okay. Let I give example to you. Let our R set is example. R is 1 1 and 2 2. This is symmetry because 1 1 is here and inverse of 1 1 is also 1 1 and here is 2 2. Okay. Then this is R1, this is R2. That I define 1 1 and 1 2. This is not symmetric. Why? Because 1 2 is here but 2 1 is not here. It implies not symmetric. Okay. Yeah. Next next type of relation is transitive relation. Transitive relation. What is transitive relation? A relation, let A be a non-empty set, A be a non-empty set, and a relation R is said to be transitive if X relate to Y, if X relate to Y and Y relate to Z, then X must relate to Z. Okay, this is our condition of transitive relation. Okay, let's give an example. A is the set of 1 2 3. Okay, then R1 we take let 1 1 1 2 2 3 and 1 3. Okay, 1 2 is there, 2 3 there, means 1 3 is also there, that is okay. Okay, so this set is our, this relation is transitive relation. Let one more example which is not transitive. Let is one example that is not transitive. Let R is 1 1 and that is 2 1 is there and 1 2 is there. Okay. This is not transitive because 2 1 is there and 1 2 is there. Then 2 2 must be there, but 2 2 can't belongs to R. 2 2 does not belongs to R. It implies not transitive. Okay. Yeah. Now I define asymmetric relation and then equivalence and partial order relation. Okay, these are the collection of some relations. Okay, 1 minute. I define now asymmetric relation. Asymmetric relation. Asymmetric relation. What is our asymmetric relation? What is this? Same theory. Let A be a non-empty set and R be a relation on A is said to be antisymmetric. Is said to be antisymmetric. Sorry, asymmetric. Asymmetric if x relate to y, then y, if x relate to y and y relate to x, then x must be equal to y. Okay, both are equal. Let's take example. Let A is 1 1 1 2. This is the asymmetric because 1 2 is here but 2 1 not is here. 1 1 is there but 1 equal to 1. Okay, yeah, this is 1 minute. This is our not a set, this is a relation R1. Okay, if I take another relation that is defined 1 1 okay, so 1 2 and 2 1. This is not asymmetric because 1 2 is here and 2 1 is here but 1 not equal to 2. It implies not a asymmetric relation. Not a asymmetric relation. Okay, this is not asymmetric. Okay, now two main, another first is equivalence relation. Equivalence relation and second is partial order relation. Partial order relation. Okay, we define these two. Okay, so first note, identity relation. Identity relation is subset of reflexive relation. Reflexive relation. Okay, this is one note. Now we define equivalence relation. Equivalence relation. A relation on A is said to be equivalence relation itself to be equivalence relation if the relation R is first one is reflexive, second one is symmetric, okay, and third one is transitive, okay. If a relation is reflexive, symmetric and transitive, then we said this relation is equivalence relation, okay. Let we take an example. What is example? Let A is set of all natural numbers, okay, and R is a relation defined as xy such that x plus y is a natural number. Okay. Yeah. Then first is reflexive. Where xy belongs to A. Okay. Yeah. First one is we check reflexive. Reflexive means xx belongs to R. If x is a natural number, then sum of these two, x plus x is 2x. 2x belongs to natural number. It implies xx goes to R. Okay. So R is reflexive. By this, R is reflexive. Next we prove second one, symmetric. Okay. Symmetric. If xy in R, it means x plus y is a natural number, n belongs to n. It implies y plus x is also belongs to n. It implies yx belongs to R. Okay. This implies our symmetric condition. Then next one is yeah. Next is transitive. Transitive means if xy and yz belongs to R. If xy belongs to R, it implies x plus y is a natural number, say n1. And if y plus z in R, it implies y plus z is a natural number, that is say n2. Okay. When we, yeah, 1 minute. X plus y is also a natural number, y plus z is also a number, then if it implies x plus z is also a natural number, say n3, okay. It implies xz belongs to R, okay. Say 1 3 belongs to R, 3 5 belongs to R, it implies 1 5 is also belongs to R because 5 plus 1 is a plus. Okay, so we have to we prove that R is reflexive, symmetric and transitive. Okay, it implies R is an equivalence relation on set A. Equivalence relation on set A. Okay, now we another define what is that partial order relation. Partial order relation. Okay, what is partial order relation? What is partial order relation? Can you tell? 1 minute. Partial order relation, same theory. Let A be a non-empty set. A relation R A relation R is said to be partial order relation. Partial order relation if R is reflexive, asymmetric, and third one is transitive. Okay. Yeah. If a relation is reflexive, asymmetric, and transitive, then we said R is our partial order relation. Okay. Now I give example of partial order relation. Let A is set of natural numbers. Okay. And R is a relation in which xy belongs to R such that x divides y. Okay. X divides y. Define. Then first we check R is reflexive or not. In reflexive, we know xx types of element comes. Then we know x divides x for every x belongs to natural number. It implies xx belongs to R or all x belongs to n. Okay. It implies R is reflexive. R is reflexive. Okay. Second one is asymmetric. Asymmetric means if xy belongs to R, then x divides y. X divides y. It implies y divides x if and only if x is equal to y. If and only if x equal to y. It implies R is asymmetric. Okay. R is asymmetric. And what is third one? Transitive. Okay. Transitive means if AB and BC are belongs to R, we have to prove AC belongs to R. AB belongs to R means A divides B, and BC belongs to R, B divides C. Then from 1 and 2, A divides C. Okay, it implies AC belongs to R. Let I give an example for transitive. 1 minute. Let 2, 6 belongs to R because 2 divides 6. Okay. And 6, 12 also divide R because 6, 12 is 6 divide 12. Then 2 12s also belongs to R because 2 divides 12, and this is called transitive. Okay. So our relation is reflexive, symmetric, asymmetric, and transitive. It implies our R is partial order relation. Partial order relation. Okay. Yeah. Okay. Now we discuss about periodic functions. Periodic function. A function f from D to a function f from A to B is said to be periodic. Periodic if f of x plus t equal to f of x or t greater than 0. Okay. or sum t greater than 0. Okay, this is our condition of periodic function. And the smallest positive value of t, positive value of t is called what? Fundamental period. Fundamental period. No, I tell you some period of some basic function. Okay, let fx is sin x. First is sin x. Then what is the graph of sin x? We know this is r and this x axis, this is y. This is 0, pi, 2 pi, okay, 3 pi, and here minus pi, minus 2 pi, minus 3 pi. Okay. Then we know what is the graph of this in the, okay, this is the graph of sine function. This is 1 and this is minus 1. Okay. Then let our point is here, x is here. Then we add x plus 2 pi. X plus 2y is here. Okay. X plus 2 pi. After that we move x, then the value of fx is same, sin x is, we get same value. Okay, so period of this function is, fundamental period is 2 pi. Okay, fundamental. Yeah, similarly for cos x, period of cos function is 2 pi. Okay, and also for fx, when fx is equal to secant x and cosecant x fx. Then we know secant function is 1 upon cos x, and 1 upon cos x is equal to 1 upon cos x plus 2 pi. Okay, this is equal to secant of x plus 2 pi. And this is equal to cosecant of x plus 2 pi. Okay, means period of secant x and cosecant x is same 2 pi. Okay, yeah, now we describe our tangent x. Fx is equal to tangent x. We know graph of tangent function is this. This is our y-axis, this is our x-axis, and here pi by 2, here 3 pi by 2, here 5 pi by 2, here 0, minus pi by 2, minus 3 pi by 2. Okay, then what is the graph of tangent function? Is this one. Okay, this one. Okay, this one. Okay, this one. Okay, this one. Then when we shift pi value, then values are become same for this one. Okay, any graph when we shift pi, then curve of tangent x graph is same. Okay, it implies period of tangent x is equal to pi. Okay, same as cot function. Period of fundamental period of tangent x and cotangent x is pi. Okay, now we define a period function for if fx is sin nx. Okay, we know period of sin x is pi, 2 pi. Okay, then period of sin nx is, period of fx is 2 pi divided by n. Okay, yeah. Same. Thank you, students. In this lecture, we cover relation one. I this in this lecture we covered relation, types of relation. Okay, questions on relation, question on relation, and periodic function, and Cartesian product. Cartesian product. Okay. Periodic function is most important topic. Okay. Thank you, students.